All right, hello everyone. My name is Ubieda. I'm the lead firmware engineer at Croxel. We provide consulting services and product development for embedded systems. And today I'm going to talk about RTIO for real-time Zephyr applications. All right, so let's go over the agenda here. What we're hoping to cover today, a quick introduction, then cover the basics of RTIO in case you don't know what it is. Probably you're familiar with it. Maybe you heard it once or twice, but let's talk about what it actually is and how it works. We're going to emphasize the async versus sync paradigms when it comes to developing applications. And we're going to see some entry examples of RTIO. On the second half of the presentation, we're going to shift our focus towards RTIO in real time. What do they really have to do with each other? We're going to look at some RTIO performance benchmarks to really know if what we're saying is what we expect it to. And finally, talk about the future of RTIO. Hopefully, we have time for Q&A. So introduction. I think I should clarify this from the start, what this presentation is and what it isn't. So what this presentation is not about, it's not about a holistic approach of how to make an application a real-time application, how to optimize all the little knobs in order to make it, the efficient as you want it to. I think that's going to come a little bit later, I'm hoping. What this presentation is about is what is RTIO, how can it help you meet these real-time constraints that you're looking for when you have this application where you need to guarantee some certain latency, some certain throughput, and so forth. So, but first let's talk back and define what is really RTIO in the first place. So RTIO stands for real-time I/O. And it's a Zephyr subsystem designed for coordinating operations with respect to external hardware devices or peripherals. Think of it like sensors, ADC peripherals, and so forth, which you want to have a streaming set of operations to be efficient and asynchronous. And the way this is modeled can be seen from this figure right here. Let's focus on RTIO client and RTIO device. That's the relationship between the client and an I/O device that you want to perform some operations on top of. And basically, how we do this is the client is clearly the one who consumes the data. Think of it as the beginning of your data pipeline, that you want to do something with the data that you're getting or the events that you're getting. And then the I/O device models or represents the hardware, peripheral, or the device that you need to perform the operations on top of. These two are communicated through two queues. As you can see, we have the submission queue and we have the completion queue. So inherently, we had a decouple between these two. So the submission queue is used by the RTIO client, in which indicates what operations it wants it to perform on the I/O device. These are generic. Some examples of these are write, read, callback, delay. And this list is not extensive, but gives you a feel for, okay, what is this really about? You want to perform a write operation on the device. You want to perform a read operation on an I/O device. And let's keep in mind that this is associated with a hardware peripheral. That is the whole point about this, right? These items are concatenated or submitted through the queue, are dispatched through what we call the RTIO executor. That essentially is just a dispatcher. It knows what operation or what submission queue item belongs to what I/O device and just sends it over for it to be processed asynchronously. The I/O device understands what this operation means. It's device specific. It knows if I want to write something, I'm going to do this action, performs it asynchronously and efficiently, and then just simply returns a completion queue item through the completion queue. As we can see, we basically cover all the elements from the RTIO. The only one that is left out is the memory pool. So inherently, you can take advantage of a memory pool owned by the RTIO client who really cares about the data in case you want to perform a read operation. So you don't need to copy memory necessarily throughout the whole application. The memory is owned by the client. It knows for how long it needs it, and it can simply say, I'm done with it. Some examples of I/O devices, I think I already gave an example, like sensors. Also, another example of an I/O device could be buses, I/O buses, SPI, I2C, I3C, and so forth. Another example could be an ADC peripheral. And example applications where this really shines has to do with low latency system or time critical systems, such as closed loop control systems. Think of this as I think I'm saying systems too much, but you get the point. For robotics, you really want to acquire the data with a controlled latency so that you can act upon it. if it slips for a bit, maybe you're not going to be able to regulate the variable. The system's simply not going to work. I said it again. And the second one is a high bandwidth data acquisition systems. Hopefully clear so far. OK. So the design goals of how, when RTIO was conceived, were this following, the following that we have here. First, minimize thread context switching, minimizing data copying, optimizing batch gathering and processing of multiple data streams, not just one I/O device, but multiple of them. And then it enables, because of this decoupling that we have, it enables you to work with user space-based applications. As a side effect that we've seen is pretty useful, the IODev abstraction serves as a bus driver abstraction, so it makes it really nice for external components that perhaps support multiple serial protocols on top of it, right? Think of it like UARTs by the ones that I already mentioned before. The way that you abstract all these operations makes it easy for you to use them interchangeably. OK, so as I mentioned, you can only operate with one I/O device. It's not only a relationship of one-to-one. You can have a single RTIO client communicate with two I/O devices. Please let me know if I'm going too fast. And as you can see, the same submission queue, SQ1, is used for both I/O devices. It is everything related to the client, and it just submits these operations. The executor dispatches them to each I/O device. They process them and just put an item in the queue to get the completion back. You can have multiple instances. RTIO client 2 communicates with I/O device 3, whereas RTIO client 1 communicates with I/O device 1 and 2. And this is not only the case that it's a one-to-many relationship to client and I/O device. You could have one I/O device, think of it as a SPI device, that is shared between different external components, and that can still work for multiple RTIO clients. That's also possible. OK, that all sounds great. Let's see how it looks in code. So if I am the RTIO client and I want to use it, what does this look like in code? Simply, you instantiate an RTIO client, as you can see, sometimes referred to as the RTIO context. The RTIO-defined macro lets you instantiate it. You specify the size of the submission queue and the completion queue. You instantiate a reader instance of the I/O device that you want to operate on. And simply, you acquire an item from the submission queue, SQE, as in submission queue event. You prepare an operation right after that, the SQE prepare write, and you just submit it. And you can choose to wait for it or not. It is designed to be asynchronous. On the consumer side, it could be in the same context, or it could be in a separate context. You can choose to consume, CQE consume as a completion queue event, or simply block on it. You can have, again, as I mentioned, you can even have it be a completely separate context, as is usually the case. Where you request the data be generated is not usually the case where you want to act upon this data or process it, right? And simply you consume it, you get the CQE, and you make up whatever you want from it. You can process it, feed it, and you release it. You do some housekeeping after you're done with it. How does this work with the memory pool? You just instantiate the RTIO client with a different macro, RTIO defined with mempool, and you just define the number of blocks, what their size is, and what their alignment is. And the only difference compared to the previous code snippet is that the operation that you would prepare, in this case is not a write, is a read operation, but it uses the pool, is that you would prepare the read operation with pool. You submit it, and you do the same thing on the consumer side, with the exception that now you can get a buffer pointer from the pool. You use it, and finally you release it. This is the way it would work. But at the end, it's a memory pool that you can size it depending on your application. You can define the number of items you need for it. And obviously, all of this depends on what you use this for. This all looks great. But as you can see now, what if we want to use it on two I/O devices? As you may know, right now, you just instantiate two reader instances of I/O devices, IODev1 and IODev2. And you can simply, does this pointer work? Yeah, and you can simply acquire two items from the submission queue, prepare their operations, and you submit them all at once. And this is going to immediately dispatch to one and the second I/O device. On the consumer side, all you need to do is just to process each item individually and do anything you want with it. Okay, that all sounds great. What about on the IO device? What you need to define primarily is the IODev API that consists of a single function called the submit one. It needs to kick off the process in a non-blocking fashion. Think of it as just starting a read operation, and you return. Now, through a callback context ideal and ISR directly, so that you minimize the overhead. You just provide the result. You say IODev SQE OK, and that's going to generate the completion event so that the application can then use it. And you return. That's how this works. To illustrate this context, this concept a little bit better, I prepared 2 sequence diagrams. One illustrated the RTIO async paradigm, and one for an equivalent if you wouldn't want to use RTIO. Does this look OK, or do I need to submit in? OK. The async paradigm, if you were to use RTIO, this is just describing what I was just saying. In the client context, you just submit the request that dispatches an IO that submit for IO device 1 that immediately or shortly after returns. And then it dispatches the operation on IO device 2, which returns. And then you just return from the submission if you don't wait for its completion. Simply, then in the same context or in a separate one, if you want to consume it elsewhere, you just wait for the completion events that, in this case, are the red contexts that we have there. And then you generate the OP, the operation has been done, and you just call the IODev complete. Same thing for the IODev 2. And finally, you just process the data. As you can see, the operation where you're requesting, the operation you're requesting on the device gets started basically almost simultaneously. Clearly, I didn't put them right next to each other so you could distinguish them. But it should be non-blocking. It should be like immediately returning. Something equivalent, there are many ways to do a sync equivalent for this. So I wanted to make it fair so that, if you use the word queue or you use like something where you're sharing the context in a sync paradigm, you're clearly going to introduce many latencies along the way. The first work item needs to be completed before the second one starts and so forth, so it doesn't really make sense. So to make it fair, what I resolved to in this case is that let's assume that you have a IO device 1 and IO device 2, and you're going to have a dedicated thread for each one of them to process their items. So the way this would work is that you submit a request, and essentially that all I should do is signal the thread of the IO device to say, start an operation. Same thing for IO device 2. You start another operation, and then the thread kicks in. Right? And it performs a synchronous operation, returns it the same way that this IO device 2 would do it. And when this returns, clearly I'm not here putting how would that information be passed on to, right? To be determined. You could use a message queue. You could use a pipe. You could use like all the primitives that Zephyr has in order for you to pass messages between each other or context. You can even borrow a pointer, all that stuff. But the thing here is that you're kind of on your own. You're defining. There are like lots of rules, and it's easier to shoot yourself in the foot if you're trying to go with this approach. Even though I'm not saying it won't work. It's just different. Okay, so where can we see RTIO in the Zephyr tree? The best example we can think of, and I believe the reason why it was invented, is to improve the sensors API. So we can see these APIs that probably do not resonate with what I just explained before. But I'm going to show you that these are just wrappers on top of the RTIO APIs that are used under the hood. We have sensor read. Oh, well, first, before going into this functions, let's go to the macros. You instantiate a sensor DT IODev, read IODev, or a stream. I'll explain what the difference is soon. But essentially, let's shift our focus into sensor read first. So you perform a reading operation. In this case, the read API is blocking. And you would just pass on the IO device, the RTIO client. In this case, it's identified as context, the buffer, and the buffer length. I want you to fill me this sensor reading with this data. It is synchronous, so therefore, what we're going to see, is it legible on the right side? Hopefully it is. OK. Well, first of all, you can see the distinction between the user space configuration and not using user space. Let's assume we're not using user space for this purpose. We simply acquire an item from the RTIO client. We prepare a read operation, and we pass on the buffer to be filled with the buffer length and so forth. So we're not using the pool in this case. And we just submit it, and immediately right after that, we call the CQE consume block. you see the consumer alongside with submission, right after one right after the another. And when it returns, this is just going to block until you have a result. When it returns, you just looks like it went back. You just pass on the buffer, check for the result, and you just return it there. The asynchronous counterpart, or the alternative, would be sensor read async mempool. So you just pass the client, you pass the I/O device, you pass any user data pointer that you want to get alongside with the operation. And as you can see, it's as simple as acquiring an item from the submission queue, preparing a read operation with a pool. You're not even passing a buffer. You should have the memory pool associated with the client. You submit it and you return. So where's the consuming context? That's where the sensor processing with callback would enter. So you would pass on the RTIO client with the callback here, and all it's doing is the second half of the operation. Consume block, it extracts the buffer from the memory pool, it releases the CQE, calls the callback, and then just immediately releases the buffer. As you can see, this is just a wrapper, and you can have variations on top of this if you wanted to. You just need to know how to use the RTIO APIs. Finally, what is streaming then? It's a special type of operation in the sensors API in which you want to generate not only one operation, you want to generate a stream of data. So essentially what you prepare is what we call the read with multi-shot. So essentially you have a configuration associated with the I/O device. Let's assume you have an output data rate, or if you're using like a FIFO watermark or something like that, you already know what operation you want to use. You just submit a multi-shot read, and it's just going to restart one after the other, following that ODR that you expect it to. And you just get submitted once, and you start getting callbacks until told otherwise. OK, everything clear this time so far? OK. Maybe this is clear, but right now I'm not really explaining what does RTIO have to do with real time. So now let's shift our focus towards that. So first, real time in I/O. OK. What is real time? In this case, the simplest way to define this, and probably there are going to be more details to be missed, but let's keep it simple, means doing the right thing at the right time. In practical terms, you have some actions you need to perform, and you need to perform it within a control or a minimum guarantee latency. Let me put you an example. I want IMU data to be streamed at 6 kilohertz, and I need them as soon as possible. But if I wait 5 milliseconds to get it, probably it's not going to regulate it's not going to be good for my system. I just made that up, but just to give you the feel that you need to have some guarantees that your system is going to be performing under the worst case scenarios as you need to. So maximum allowed latency has to do a lot with the reaction time, which is the difference between the event happening. As we can see here, we have an oscilloscope capture. Yellow line means an interrupt line of an IMU. So it's just generated an ODR, like a data ready interrupt, every time it gets you one. And the blue line is just a chiplet line, which is communicated over SPI. So essentially, we can see every time you get a falling edge, you're really doing a SPI transaction. So you want to extract this. So the difference in this case, or the reaction time in this case, will be the difference between this rising edge and this first falling edge, where the application starts pulling the data from the external device. The bus latency would be, I guess, the difference between this rising edge and the completion of it. So at this point, the information has been completely transferred over your application, and you can act upon it. And jitter is, obviously, when you have this streaming and running over time, you're going to have some inconsistencies. It's inherent to an embedded system that sometimes you're going to be performing slightly later than others. And the important thing here for real-time constraints is that you need to have that control within a margin. You have some minimum guarantees. The other side of this is having enough CPU cycles to perform all the required actions. And just to make one clear observation is that this starts at the hardware level. This is not like you pick anything and you make it work. Clearly, what you want to do is correctly size for your constraints, your performance requirements, and then just try to make the best in the firmware in order to make use of those hardware features that you've enabled through the design. Which in this case, CPU cycles involves everything in the process. Let's assume that you collect the data, you process it, you transport it, everything. You need to have enough cycles to complete everything. And you should have some margin on top of that, right? And this should be validated on their worst case scenarios. And oftentimes, like the bottlenecks of this have to do with the serial bus interfaces. In this case, for instance, let's assume that we want to evaluate what the performance or the margin for this picture is. Let's assume the requirement is, just making that up again, the requirement is to be able to keep up with the interrupts that are coming, to reliably react to these interrupts so you can prevent missing samples and you can process them accordingly, right? So in this case, we would have a bus latency. In the worst case scenario, we can see some jittering. And the worst case kind of like would fall here. And we have some bus margin. But that's not a lot, I guess. Depends on how did you test that. If you enable Bluetooth, if you enable networking stack. It's important to stress test that in order to validate that what you're seeing is real, is the real margin of your system. In this case, obviously, I'm not considering the CPU latency. It's like, OK, the data has been pulled over serial, in this case SPI, and then you need to act upon it. So obviously, you need to account for that. But I'm just illustrating the context, the concept here. And what you want to happen is I guess your left side, where we zoom in at the 5 microseconds per division here, and we can see some jittering going back and forth. What you definitely don't want to happen is the right side where the interrupt happens, and there is some point where the jitter goes even beyond the next interrupt. So in this case, you're not able to keep up with the data pace. And clearly in applications, you don't need to worry about one data stream. You oftentimes have multiple data streams that you then need to gather them all, fuse them, process them, perform algorithm calculations, everything, anything that your application may need, but you just need to look at this from a holistic perspective, making sure that everything is in place, and obviously zooming in the most time-critical portion. What's your bottleneck? And look into that. So that is our real-time in I/O. Now let's flip this over and see what does RTIO have to do with real-time. As I mentioned, the design goals for this was to minimize the overhead, memory copying, data conversions, context swapping, and whatnot, and also has been designed for real-time. What does this mean? It means it's designed to take advantage of hardware features. Some of these examples would be like FIFO, DMA, peripheral connections, and whatnot. You need to use those hardware features to be able to keep up, and if you have them, why wouldn't you, right? It is really easy to set up simultaneous streams of data, as I mentioned before, with the async paradigm. And it does guarantee decoupling of data acquisition and processing. And this is important because oftentimes the critical part of your system is just timely acquiring that data. Maybe processing them is not that time critical. You just need to make sure that you have enough, you don't lose any sample, and you perform the calculations when you need them to. But oftentimes the acquisition side is the most time critical, so this is very well suited for that. As a result, we have reduced jitter, and as a result, we have predictable latency, or much more predictable latency, and less CPU load. And that all sounds great, but we need to back that information with data. So I spent a lot of time performing these benchmarks, and I'll explain what my setup was and what the results are, and we can talk about them. So the device under test that I prepared was simply a Cortex-M running at 150 megahertz, which is an NXP MCXN 947. And I had 3 sensors. One IMU running at 3200 hertz or at 6400 hertz on a dedicated SPI bus. And I had 2 accelerometers running at 100 or 400 hertz. If you ask me, why would you have an IMU and 2 accelerometers? The only answer is because I have them laying around. It's just a flow of data, and they had entry support, so let's just use this. But in real time, in an actual application, you may want to have an IMU flowing, having data streaming alongside with an optical flow sensor and a time-of-flight sensor, and many other things. It's just to illustrate the data flow context and how can we put this under stress and see what the results we get with. I tried this with so in this time I didn't use We didn't spin a custom board. This is really ugly. I actually used breakout boards that I connected. As you can see, the red one and the green one on the left are the two ADXLs, 345. And I even had to make an adapter board to connect the IMU. It's really ugly, I understand, but
beautiful.
That's just not true. Okay, so how do we measure the CPU load? We measure the CPU load, we measure the latency, and we measure the jitter. We use two tools to measure this. The first one is integrated in Zephyr. You can get it for free, and is the CPU load utility. You enable it, and you can get periodical reports or results of the worst case within that time window, of how long did the CPU stayed in the idle task versus elsewhere. And as you can see those logging outputs being displayed there through the shell. And I double-checked that information with the tracing utility with system view in order to make sure, hey, this information really makes sense. For measuring jitter, I went the good old way, which is setting up an oscilloscope. You set up the trigger for the rising edge. Let me see if I can illustrate this. The rising edge of the interrupt is where the trigger is set up. You can clearly see it here. And I just use another probe to scope the chip select line. And I set the persistence to infinite. So essentially, you let it running and you see all the variations as you can see here. And I took the result, in this case for jittering, it's just the variation for the last rising edge. In this case, you can see that the delta, I'm really bad with this, my pulse and stuff, the BX minus AX is 44 microseconds. So you can see kind of like a variation between this rising edge and this last rising edge, which is kind of an hour line. But it happened once, right? That's the point. Design the system for the worst case scenario. And for measuring bus latency, I guess I could have used the same scope capture and have it be persistent, but I just didn't do that. And I set up a logic analyzer and just measure what the overall performance was through the rising edge and the last rising edge for the chiplet line. This is just essentially a discrete information. You could do many things with that. You can accumulate the jitter plus the latency. In this case, I didn't go that far, just to get a feel for what the actual latency is. But you can certainly do that. OK, so I guess finally, these are the table with the results that I got. And the testing scenarios are on the left. Please don't look at the data yet. Just let's focus on the testing scenarios. We have the IMU running at 3200 hertz or at 6400 hertz. And we have combinations, so permutations of the two ADXLs running. So either not running, so exclusively running, the IMU exclusively running, or IMU plus 1 as accelerometer running at 100 hertz, or this IMU plus the two accelerometers running at 100 hertz. You get the gist, right? So we expand that pattern for 400 hertz as well for one accelerometer and two, and for 6400 hertz, exclusively running, or one or two accelerometers, or one or two accelerometers running at 100 and 400 hertz, respectively. So the data that I got basically categorizes CPU load, latency, and jitter. For CPU load, we can see that the thread-based solution, the same one that I described with the sync paradigm, I had separate threads for each one of these, was that it is slightly and consistently slightly bigger for a thread-based solution versus an RTIO-based solution. We can see, give or take from 6 to 8%. It's what we're looking at here. For latency, they're kind of similar, slightly longer for the thread-based solution, as we can see, but it isn't that much. But the biggest difference of these RTIO-based solution and the thread-based solution is the jitter. As you can see, it is significantly lower for an RTIO-based solution, give or take 2, 3, or even 4 times that. The devil's in the details. How do you configure this? What are the threads priority? And all this stuff. Obviously, that is the different knots that we need to pull, but the message here is that with an RTIO-based solution, you perform actions without overhead, or like the closest to the immediate event that they are, because they're not blocking, you basically are getting what you're getting. And the callback would immediately return something. And as we can see, it is a lot more consistent with an RTIO-based solution. Worst case, as you can see, with the two accelerometers running at 400 hertz and 3200 hertz in IMU, 155 microseconds and 175 microseconds. I guess I could have done more extensively testing, but I just ran out of time. So these are the results for now. But as you can see, the jitter could even be twice what the latency is. So that is, pretty significant. And it's worth saying for the IMU running at 6400 hertz, the thread-based solution was not able to keep up with the stream when you start adding the simultaneous components. Now, we need to be fair. Probably I wouldn't design a system that right off the bat you would have 80% CPU load. That's not a good practice. But the message here is that with an RTIO-based solution, you're just able to push the boundaries further. You're able to get more predictable results. And because we're thinking of RTIO, we need to talk about the future. Is this just a sensors thing, or is this something that could be more than that? So the future of RTIO and what we believe is the future of RTIO, number one is extend existing support. We're starting to integrate support for sensors, what we call the sensor MAL B2, the read, decode, and streaming APIs that I just showed you, and support for bus drivers. More bus drivers means they have native support, and you're going to be able to achieve this performance without extra overheads. And second, expand to more applications. There's an in-flight PR that is introducing RTIO support for ADC. Same use case, data streaming. You want to stream a data of ADC samples, and you want to do it efficiently. It integrates with RTIO. We have discussions with the BDO subsystem collaborators that they want to introduce RTIO as a potential option for their data pipeline processing. So they capture images, and they want to do it efficiently. They're interested in RTIO. And also, there seems to be some interesting audio, but we have no timeline for that. I think that we're very early in those discussions. Finally, one thing that we are very interested in is the ability to perform direct peripheral interconnections. What does that mean? A GPU interrupt yields to a SPI transfer. You don't need CPU intervention if you can coordinate directly these two things. It's really hard to make it abstract. Every vendor have their own way to do that, but we're looking into that, and we are very interested in making this happen because we believe these hardware enablement capabilities is what really makes a difference. The software optimizations are great, and you can get predictable results with that, but we see these as incremental improvements. Really, the hardware enablements are what it's going to take the next step for your application. The future of RTIO also involves you. If you're interested in what you heard, feel free to engage in the Zephyr community. We are very welcoming, and that's not a joke. You can use the RTIO channel in Discord, engage in conversations, have questions. Do you have an application you think RTIO would be a good fit? We're very eager to hear about that, and we're open to discuss that. And also, if you want to have sessions with calls and conversations, we have a sensors working group on a biweekly cadence, Mondays at 7 a.m. Pacific time. Alternatively, at Croxel, we love Zephyr. So if you want to talk about it, feel free to scan this QR code. And yeah, well, hopefully we can help you in application or just chime in some ideas you may have. We're open to that as well. So hopefully we have some time for Q&A. I think I spoke too much. Does anybody have any question? Yes.
Great job. No, it was just, you seem tired, so I wanted to energy.
Yeah, I think I need to drink some water. You will.
Have you given any thoughts about when you showed the CQE blocking right, when you basically say, hey, I'm going to block here and wait for a response?
Yeah. Let me see if I can pull that back.
Do you have any ideas about how to do this in a way that is thread safe, right? Because the concern is if you ever have two threads calling that, you don't know who's getting what response.
OK, that's a very good question. And I think it centers around the concept of the client and the I/O device, right? I guess under the hood, RTIO uses the multi-producer single consumer queue. So in the consumption side, it is only designed for a single client that uses the data. So it doesn't really support right now multiple consumers. I'm not opposed to that idea, but that's just the way it is. And the fact that it is lockless, it makes it more performance friendly. So it is what it is for now. Yeah.
Any thoughts to streaming input devices from the input subsystem as well?
I think no, I haven't thought about that. We'd be open. Reach out, engage. Let's build it together, guys. Yes?
I'm wondering how the RTIO subsystem manages like bus contention issues when there's multiple streams coming from the same 5 bus or bus.
That's very good. So actually, let's go back to here. I got to be honest with you. I simplified these slides. I didn't want them to be so complicated. But OK. I guess you're asking the opposite of this left slide. So you have two clients wanting to use the same I/O device. They're submitting requests, and you want to process them, such as the diagram that I show you, two sensors using the same SPI bus. So internally, the I/O devices have a queue on its own. So they receive the submission, and essentially they're just going to pop in off items from the queue and processing them in an unblocking fashion. But until you've completed the one before, you're not going to get the next one. So that's how it's handled, that contention use case. So it is covered. OK, let's go. I think there are some in the back, but yeah, please go on.
Maybe related to that, is there any way that I could, like, have multiple things I want to read from, and like here are my requirements, and like it could, tell me if this is even possible to like meet my deadlines? But, is there any kind of like schedulers surrounding this, or is it just like as fast as possible?
So that's a very complicated question. So the question is there any intuitive way to know if I have these requirements, if this system, is this even possible, or am I close to the edge or something? I don't have a good answer for that, unfortunately. You can kind of like get an intuition for, and this was a really interesting exercise on my end. It's like toggling a GPIO with the Zephyr APIs. How many cycles does that take versus just directly accessing, the pointer and changing that? And it's a difference. So Zephyr does provide some abstractions which make it good, but at the end it does it's like you give and take. You have abstractions, but at the same time you do that. The best way to do that is to simply, I encourage you to have a setup, simply, similar to what I had. Let me put that picture again, the setup. That. OK, so simply if you have some breakout sensors, you have a development kit for the target that you think you want to use the shell. The shell is very useful. You don't need to program things. If they work internally, you have the sensor stream shell commands. You can, actually, this is not upstream yet. I used it. I enabled this for this presentation, but I'll upstream it real soon where you can enable multiple streams at once. That's how I use this. Probably that's going to be useful. You just use the tracing, use the CPU load, you measure the latency. It shouldn't be too much work, I'm hoping. But yeah, unfortunately, the best way to know that is to try it. OK, let's go. But just quick, how long do we have? OK. I guess 2 to 3 more questions. What's your question?
Keep it short. I'm wondering how you can deal with latencies relating to like a SPI bus or an I2C bus, because I'm struggling with the SPI driver that doesn't return very consistently. I'm having some jitter with that. I'm wondering how you optimize around peripherals that behave that way.
So which target are you using? OK, that's fine. Maybe a bug in the SPI driver. That's the first thing I'd look into. But yeah, if you can share what you can share. I'm not asking you to disclose any information. But most likely that's the first place I'd look into that. And the tracing utility is really good for that because you can see where your cycles are going. Right? It's like it is spending too much time holding the semaphore, or is doing this. It's giving the same semaphore multiple times, and that's where my cycles. It's a really good, I guess, other than I suspect there's a bug in the SPI driver. That's what I would do. OK, so two more questions.
Does this require re-architecting the sensor driver to support the RTIO model?
That's a very good question. Yes, and that is part of the endeavor that the sensor working group, which I'm a part of, is currently in the making of. I don't know if you guys are familiar with the sensor, the first model, the fetch and get. OK, as you may interact, it's not really useful or very friendly with this type of operations. You have 2 values where the integer and the decimal part, and it just converts it and then converts it back. The memory is hosted in the driver. You need to copy it. There, I don't want to ramble about that right now, but it's we needed this. OK, last question.
Thinking about request and thinking about storage devices. Is this approach applicable for storage devices?
For storage devices. OK, so let me think about that. As in, you have a logger application you want to stream logging.
I have file system. I would like to make it much faster. Can I use this approach to make my file system faster?
I would say yes, but probably there's not support for that in the tree. Yeah, if you want to take that and answer.
Mostly all of this is based So as long as your memory device allows you to initiate a read and then fires an interrupt on completion of the read, then yes, this will work. You're basically just bound on, can I get some kind of interrupt event when the operation is done?
Yeah, that's a great answer. Does that answer your question? Okay. Sorry, we ran out of time. Thanks so much for your time. And yeah, reach us out if you have any questions.